Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
Alrighty, let's take a look at lesson 4.2.1. This is called proportional relationships, and this is going to introduce you to the big idea of seventh grade about what constitutes a proportional situation. Whenever we're solving problems, if we can recognize that a problem is proportional in nature, then that really limits the number of ways that we can solve that problem, which actually makes it a lot easier to solve the problems because you know there will be a couple of go-to strategies that you could use. So in this lesson, this is meant to introduce this idea of what you will see and how you will recognize when a situation is proportional in nature. So to get us started, let's first make sure that we understand what we mean by a proportion. So a proportion is a situation in which two ratios are equivalent to each other. So this is not like the word problem definition of how you recognize a proportion. Just the fact that something is proportional means that if you were to take data from that situation and compare them, it would form a couple of ratios that would be equivalent. So let's just talk about what we mean by two equivalent ratios. If we take the fraction 2/3, that's equivalent to 4/6. Excuse me. This combined makes a proportion. And so this is basically the definition of a proportion. Excuse me, hold on. Okay, let's get back to this. So this is the definition of a proportion. If we take any two fractions that are equivalent to each other, like let me show you an example where you would involve a unit rate. So if you had like something that costs $5 for every 1 kilogram, that means that if you buy 3 kilograms, you would spend $15. That is putting into context what these numbers represent, and this situation is absolutely proportional in nature because 5/1 is equivalent to 15/3. So now proportional reasoning. Proportional reasoning involves using this knowledge to solve for a piece of missing information. So let's go back. What do I have down here? I have something that looks like the coat of arms. All right, we'll get to that in a second. All right, so where are we? If I say 2/3 is equal to x/6, since you know that they're equal, then you know that this ratio has to be proportional to this ratio. So we know there's some process that we can use to figure out what x is equal to. And so we have learned about the giant one, where you know that if you multiply 3 times 2, you'll get 6. Therefore, you'll multiply 2 times 2 to find out the unknown number, which in this case is known to be 4. And then, we do the same thing here. If we say 5/1 is equal to 15/x, you look at that and say, okay, so if it's $5 for 1 kilogram, how many kilograms can you get for $15? Well, giant one says 5 times 3 is 15, and 1 times 3 will have to give you 3 kilograms. So this process is referred to as proportional reasoning when you're using it to solve a problem. Okay, I'm going to get rid of this because I obviously don't remember what I had done there. But the giant one is one strategy that you can use, but there's another strategy where we employ kind of that idea of the coat of arms where we cross multiply. So if I cross multiply here, we will get 3 times x is equal to 3x, and 2 times 6 is equal to 6. And now, to figure out what x is equal to, you just have to solve this equation where we divide each side by 3, and you get x must be equal to 2. Now, why do we know that this works to do that? Well, one thing, sorry about this, I'm just spacing this out a little bit more. Okay, there we go. That's, I don't know, my OCD is taking over there. This is something that at first glance, you maybe don't notice this up two fractions that are equivalent to each other. But look what happens when you cross multiply. 2 times 6 is 12, and 3 times 4 is 12. So the cross products, anytime you've got equivalent fractions, are always going to be equal to each other. That's a basic foundation of proportional reasoning. Same thing here, 15 times 3 is 15, and 1 times 15 is 15. So with that in mind, if we know whenever two fractions are equivalent to each other, their cross products will be equal, then I can use that as a part of my proportional reasoning. I will cross multiply, and this says 5x, right? 5 times x will be equal to 1 times 15. And now what number do you multiply times 5 to give you 15 for an answer? Well, we can use our algebraic reasoning now to say that x has to be equal to 3, which gives us the same number that we had on the bottom here. So proportions, two ratios that are equivalent to each other. When we're solving problems, we'll have to create those two ratios. And generally, when we're solving problems, one part of the ratio is missing, and we'll solve it using proportional reasoning. All right, so grocery stores often advertise special prices for fruits and vegetables that are in season. You might see a sign that says, special today, buy 2 pounds of apples for $1.29. Would you use that information to predict how much you need to pay if you want to buy, say, 6 pounds of apples or just 1 pound of apples? The way that the cost of apples grows or shrinks allows you to use a variety of different strategies to predict and estimate prices for different amounts of apples. In this section, you will explore different kinds of growth patterns. You will use those patterns to develop strategies for making predictions and deciding if answers are reasonable. As you work today, ask yourself these questions to help you identify different patterns. How are the entries in the table related? Can I double the values? And what patterns can I see in the graph? All right, so we're going to start with a situation here where Gustavo, 5 years ago, his grandmother put some money into a savings account. So let's highlight Gustavo's grandmother put some money into the birthday account, or into a savings account for his birthday. The amount is simple interest, which we'll get into the details of how simple interest works a little bit later. And now, after 5 years, the account is worth $500. I'm going to underline that. After 5 years, it's worth $500. Gustavo predicts that if he doesn't deposit or withdraw any money from this account, the account balance should be $1,000 5 years from now, right? So he's, what is he looking at here? How do you think Gustavo made his prediction? 5 years, it's been in the account and it's worth $50 or $500. He thinks in another 5 years, it'll go up to $1,000. How do you think Gustavo made that? What was he thinking happened with the money and will happen with the money? So my thinking is this. 5 years ago, Grandma put money into an account. In 5 years, that would be like doubling the amount of time, correct? So it's been 5 years. He's saying in another 5 years would be 10 years after grandmother deposited the amount. So I think what he's going with is the fact that the number of years has doubled. So he's thinking that the amount of money in the account would double as well. So, I mean, I guess maybe that kind of makes sense, but I think we need to have a little bit more information. Like, for instance, how much money did his grandmother put into the account in the first place? That would be information we would need to know whether or not the dollar amounts are doubling. And then even then, you might be a little bit troubled by the logic involved in this. So let's do a little deeper dive into this problem. Last week, Gustavo got his bank statement in the mail. He was surprised to see a graph that showed that although his balance was growing at a steady rate, the bank predicted that in 5 years his account would only be $600, not $1,000. What is going on? He wondered. Why isn't my money growing the way I want it to, or the way I think it should? You don't have your team with you right now, but you can think about how much Gustavo's account appears to be growing every single year. And I've created this kind of a number line to sort of represent that situation. Now, I'll give you a tip. The bank is not wrong, okay? They're not making any mistakes with the account balances. They know what's going on with these accounts, and they can pretty accurately predict the dollar amounts in 5, 10, 15, 20 years because they understand the mathematics. This is what they do for a living. So let's take a look at this number line. Might be a good idea for you to write this number line into your journal and take a look and see how it's growing. Grandmother put money at the start. We don't know how much she put in. 5 years passed by. Although his bank balance was growing at a steady rate, that means it's growing at a constant rate. It's not changing. It's not like one year he made $100, the next year he only made 10. It's growing steadily or at a constant rate. So let's think about our scaling processes that we've learned, that we've done in our homework a few times. So from here to here, how much did it go up? To go from here to here, how much did it go up? How much does it appear to be going up per year? Go ahead and pause and then jot down the answer to this question. How does it appear to be growing per year, and why might this account be growing in a different way than he had expected? Go ahead and pause and take a few minutes to write this down, fill it in, and then write a little response. Okay, so that the second question is, we still probably need to do a little bit more investigating to answer that question. But I think we can answer the first part, right? How much does it appear to be growing? Let's go from 500 to 600. It kind of looks like, what is that? 1, 2, 3, 4, 5 steps. So in 5 years, it grew $100. So how much is it growing per year? If you said it's growing by about $20 per year, that would be the unit rate, correct? That does appear to be the answer. The account appears to be growing by $20 per year. So that would make this 520. This would be 540. This would be 560. And this would be 580. And if we work backwards, we should be able to figure out how much his grandmother put into the account, right? This would be $480. This would be $460. This would be $440. This would be $420, which makes it look like at the beginning, grandmother must have deposited $400. If the bank is correct and it is growing at a steady rate, and the bank's prediction is correct that it'll be $600 at the end of 10 years after the grandmother had deposited this money. All right, so Gustavo decided to look more carefully at his balances for the last few years to see if the bank's prediction might have been a mistake. So he put together this table. So this table kind of agrees with what we put on that number line, right? Where year 2 was 440, year 3 was 460, year 4 was 480, and of course year 5 was 500. So does it appear to be growing the way we thought it was? How does the bank balance appear to be growing? Absolutely. It's increasing by $28 per year, which is what we said we thought it was doing. Does Gustavo's money seem to be doubling as the number of years doubles? Like, does it double to go from 2 to 4 years? If so, then that should say 880, not 480. So I'm thinking, no, that's not really what's happening there. It's not doubling the situation. Is the bank's prediction a mistake? Well, based on the fact that this agrees with what we had said here in this number line, and the bank was saying after year 10 it should be 600, I would say no. I would say the bank's prediction does appear to be accurate. Okay, so once Gustavo saw the balances written in the table, he decided to take a closer look at the graph that the bank has provided so he could see. And this is, you can download or take a look at this resource page that is on the classroom. Find the graph on the classroom. There's what the graph looks like, okay? There is additional information about Gustavo's account that you can tell from looking at this graph. Now remember how we used that number line to figure out how much his grandmother must have put into the account? Now look at the year 0 on the graph. So time years after being deposited, right? This is 1 year after the deposit. That's 2, that's 3, that's 4, that's 5. The 5th year appears to match up with 500, right? Let me go ahead and show that if we take a straight line here to where it touches the line, and then, oh, stop it. And then we take a straight line there, it looks like it's going down to the 5, right? Now, if I do this perfectly, and it doesn't get all messed up, yes, that's perfect. Couldn't be any better. So yeah, that agrees with the bank statement. And we could use that for all these different amounts. If we would go to 300, Wait, there is no 300. I guess it's not easy to do anything else because we don't have it. We're counting by hundreds. That's not a great way of doing it, but it does agree with something that we showed, right? It shows us how much grandmother deposited. So let's just read through this problem. There is additional information about Gustavo's account. For example, what was his starting balance? What does it look like? Right here. How much did grandma put in year zero? That would have been $400, right? And we know that it grows 100 in 5 years because of this. In year 5, it went to $500. And so how much do we expect it to be in year 10? We expect it to go up to $600. Gustavo had assumed his money would double after 10 years, but he was wrong. What would the graph look like if that were true? Using a different color, add a line to the graph that represents what Gustavo was thinking. All right, so this is where it would be really good for you to be able to print this off and create this graph. But if you're not able to, then you could just watch what I'm doing here. So I put blue dots. That's going to represent our new line. Okay. So same exact graph. Year 0, $400. Year 5, $500. Year 10 shows $600. But Gustavo thought year 10 was going to be 1,000 because he thought the number would double. So I'm going to go ahead and put a line here between those 2 points. Let me color it blue since my dots are blue. And I'm going to connect these points. And I'm going to keep the trend going. And I'm going to keep the trend going. And I'm going to keep the trend going. And notice what happens where that line actually touches the graph in the year that grandmother deposited the money. Oh, wrong color. Sorry. Let's get our color coordination right. There it is. Okay, so this is the origin of the graph, right? Where x is equal to 0 and y is equal to 0. So according to Gustavo's thinking, if this were actually true that the number would double after another 5 years, that would have meant 0, 0, it would have to be $0 in year 0. It would have to be $100 in year 1, $200 in year 2, $300 in year 3, $400 in year 4. Of course, we know it was $500 in year 5, but then $600 in year 6, $700 in year 7, and so on and so on and so on. Does that even make sense? Is it possible that Gustavo's grandmother could have put 0 money in the account and had it grow over time? That's where we get to this part. Is it possible that Gustavo's account had $0 in it in year 0? And the answer to that is no. I mean, you need to have money deposited into an account before you can open it. You don't just open an account with nothing in it and have the bank start giving you money. You've got to start with money in it, and then it starts earning interest over time. So this is not even remotely possible for that to be the case. All right, so let's shift gears for a second. Hold on for a second. I got something to take care of. Okay, so let's take a look at a different type of a situation. Who is this? Sonia. When filling her bird feeder, Sonia noticed that she paid $27 for 4 pounds of bird seed. Next time, I'm going to buy 8 pounds instead so I can make it through the spring. That should cost me $54. So this assumption that doubling the amount of bird seed would double the price, does that make sense? How much would you predict 2 pounds of bird seed would cost? All right. So let's just think about this. Let's think about a unit rate. How do we find unit rates? She spent $27 for 4 pounds. And so if you're going to figure out how much that is per pound, then you take $27 and divide it by 4. And this is an example of proportional reasoning right here. These are 2 equivalent ratios. Whenever you find something that we refer to as a unit rate, this is what we are doing. It's based on the idea that these 2 fractions are equivalent to each other. And if you want to buy 1 pound instead of 4 pounds, you would take 4 and divide it by 4, and that would give you the 1, correct? So if we divide this number by 4, you get 1. So we'll have to do the same thing here. divide the 27 by 4. And when we do that, you get $6.75. That would be what we would call the unit rate for this particular situation. So with that being the case, how much would $2, I'm sorry, 2 pounds of the birdseed cost? Well, you'd multiply 675 times 2, correct? And $6.75 times 2 is $13.50. If you were to use that to justify her thinking that the price would double, then you could just multiply 8 times $6.75, and let's check and see what that is on the calculator. 8 times $6.75 is $54. There you go. So she is correct. The assumption that it would double was correct. So I guess the question, the big question is, how is this different than Gustavo's situation? Why is this one doubling, but in Gustavo's case, it didn't double? That gets to the very nature of what proportional reasoning is all about and what it means to be a proportion. So to check her assumption, she found a receipt for 1 pound of birdseed. She decided to make this table, which is started below. So she's bought 1 pound before and paid $6.75. That's the price we said was the price per pound or the unit rate. She's also purchased 4 pounds, which 4 times $6.75, let's just prove that that's correct. 6.75 times 4 is indeed equal to 27. Good. Okay, so now what I'd like for you to do is copy this table down and fill in all the dollar amounts. How much would she pay for 2 pounds, for 3 pounds, for 5, 6? We've actually got the number for 8 pounds, so we can just go ahead and reveal that as well. And then how much would it cost if she bought 0 pounds of birdseed? Okay. Then once you've got that completed, think about answering these 2 questions. How do the amounts in the table grow? And does the table confirm Sonia's doubling relationship? Okay. So I'm going to pause. You go ahead and fill that in and answer those 2 questions. Alrighty, so I'm going to do the big reveal. So if you have not paused the video and filled in your table, please do so now. Otherwise, you're going to see all the answers, and it would take all the fun out of doing this work. So here's the big reveal. We all know if you buy no pounds of birdseed, you're not going to spend any money. That is an essential piece of information that makes this a proportion. It's the fact that 0, 0 applies. If you don't buy anything, you don't pay anything. The second part is the fact that this table is now going to grow according to a pattern or a constant growth rate, which is the unit rate in this particular situation. If you multiply 1 times 6.75, you get 6.75. If you multiply 2 times 6.75, you get $13.50. If you multiply 3 times 6.75, you get $20.25. If you multiply 5 times 675, you get $33.75, and 6 times 675 is $40.50. Now also notice this, when you double the 2, you get the 4. When you double $13.50, you get $27. If you double the 4, you get 8. And when you double the 27, you get 54. So that doubling action also comes into play when you've got a proportional situation. So we can say that the amounts grow by 675, which is a unit rate, which is a constant growth rate. And does the table confirm Sonia's doubling relationship? Yeah, it does. So first, we know that she thought it was going to double and be $54, and when we multiply 8 times 675, it gets 54. It's $54. And then what I highlighted here in yellow is the idea that if you double 1 pound, it gives you 2 pounds. If you double 2 pounds, it gives you 4. You double 4, it gives 8, and so on and so forth. In fact, you could even look at this doubling. If you double the 3 pounds, you get 6. So what is 2 times 20, 25? 40, 50, right? So it works all over the place. Here are the graphs of the 2 situations. This is Sonia's birdseed problem. This is Gustavo's bank account college fund situation. Notice the difference between the 2 graphs. Take a look at these and jot down a note. What do these 2 graphs have in common, and what do they have that is different? Okay? Take a look at it. You don't necessarily have to copy them into your journal. Just think about this. What do these 2 graphs have in common, and what is different about them? Because when we're done with this, there's going to be some basic things that you're going to be looking for whenever you look at a situation to tell whether or not it's proportional or not. And the graph is one of the easiest things you can look at and tell right away whether or not it's proportional or not. Okay? So if you're looking at this two graphs, what do they have in common? Well, really just one thing that I see that they have in common, and that is that both of them involve straight lines. Now, in a graph, what the straight line means is that it's growing by a constant rate. This one was growing by a rate, let me do this guy, of $20 per year, okay? And this one was growing by a constant rate, which was $6.75 per pound. So the fact that there's a constant growth rate or a unit rate kind of a situation means you're going to have a graph with a straight line. Always happens. If it wasn't a constant growth rate, your graph would be doing something like this, or this, then this, then this, then that kind of a thing. And what is different about them? Well, where did this guy start and where did this guy start? Those are the key differences. Gustavo started at $400 and then grew every year after that. Sonia's starts at 0 because, once again, if you don't buy any birdseed, no pounds, then you don't spend any money. You just walk into the store and you walk back out and you cut all your money. Okay, so that's a key element of what makes proportion a proportion. So how do you do the differences explain why doubling works in one situation and not in the other? Well, Gustavo's account, it started with 400, so doubling does not work in his situation. So that brings us to the proportional relationships and what is happening whenever you have a proportion. So that's what I thought. Okay, so I'm going to have you copy this down. Please pause this and write down this information. This is essential for proportional reasoning, and it's so important. I'm going to underline this section right here, and I've got this numbered 1, 2, and 3. Okay, so whenever we're thinking about whether or not a situation is proportional or not, this is what you need to consider. If there is a constant growth rate, that it's the need for proportionality. All proportions have a constant growth rate. And as you saw up here, both of those had a constant growth rate. So Gustavo's situation did fulfill that requirement for proportionality. But this is where things start to change. There's a scale factor or multiplier that is applied in the situation, which kind of you think of as that unit rate. It's not always the unit rate, okay? And then this is the other big key. 0, 0 applies to the situation. So I would say the two biggest things to be aware of is that there's a constant growth rate or a unit rate, and 0, 0 applies. Those two are the big ideas that fit in with proportional reasoning. And once you read through a problem and you see, oh yes, okay, there is a constant growth rate and 0, 0 does make sense in this situation, now you can set up the problem, set up your information and your data into a proportion, and you can either use giant 1, you can find a unit rate, or you can use that cross multiplying thing that I showed you at the beginning of this lesson. I'm going to move on. If you need to pause it to copy the rest of this down, please do, and then unpause. All right, so here are the last two problems, and your check for understanding today is going to follow this model, okay? So when you're making a prediction, it is important to be able to recognize whether a situation is proportional or not. So what you need to do is read through these situations and then declare whether or not you think it is a proportional situation or not. And I'm not going to have you justify your answer in the check for understanding, but it's good for you to be able to justify your answer in your own head before you make your decision. So let's look at A together. It says Carlos wants to buy some new video games. Each game he buys costs him $36. Is the relationship between the number of games Carlos buys and the total price proportional? So I'm going to ask two things. Is there a constant unit rate? where the games always cost the same amount every single time. So the amount of growth would be the same when he's buying 1 game versus 2 games versus 3 games versus 4 games. If that is correct, then we move on to the second part. If Carlos buys no video games, does he spend $0? In this case, the answer is yes. So we're looking for, is there a constant growth rate? Yes or no? In this case, it was yes. Is 0, 0 apply to this situation? Yes or no? In this case, the answer is yes. So we can declare this is, in fact, a proportional situation. And it would be defined, if we wanted to create a rule for it, as y is equal to 30x times x, or 36 times x, where x is the number of video games that he would buy, and y would be the total cost. So if he buys 10 games, that's $360. If he buys 5 games, that would be $180. If he buys 2 games, that would be $72. If he buys 1 game, that would be $36. And of course, if he chooses not to buy anything, he spends no money. Now let's look at this one. A single ticket to a concert costs $56, while buying 5 tickets costs $250. Is this proportional in nature? So one way to find out is multiply 56 times 5. Does 56 times 5 equal 250? Because that would be your whole multiplier thing going on. And in this case, it looks like it doesn't. So while 0, 0 does appear to apply here, right? Because if you buy no tickets, you spend no money. It's the constant growth rate kind of a thing. Five tickets cost $250. The unit rate should have been $50 per ticket. And if that's what they said here, then we would have said, yes, this is proportional. But it's supposed to be 56, so there must have been some kind of a discount along the way. So that means that there's no constant growth rate. So there'd be no way for us to create this kind of proportional rule to figure out the pricing. They've obviously given an incentive to buy more tickets by lowering the price a little bit. So these are just 2 situations and things that you can look for. There might be other things that keep you from deciding it's proportional other than this. But we'll explore those as time goes on, and we'll see a lot of different situations that make it non-proportional. But the same thing always happens when it is proportional. Constant growth rates and 0, 0 applies. All right, so a little kind of a long lesson, but it's okay because this was a very important lesson to lay the groundwork and foundation for much of the work that we're going to be doing for the rest of 7th grade. Okay, all right, bye. Bye.
Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.